In this lecture, we are going to discuss Monte Carlo integration, which is a key aspect for writing a Monte Carlo path tracer and important for both direct and indirect illumination. Computer graphics rendering involves integration. For the reflection equation, you need to integrate over the incident illumination. For the rendering equation, it is an integral equation. Many of the sophisticated shading effects in this course involve integrals, effects such as anti-aliasing, soft shadows, indirect illumination, or caustics. Here is an example of soft shadows. This is from a paper I wrote 20 years ago. You can see that under an area light source, this plant gives rise to these intricate soft shadows that have a lot of shadow detail in them. Effectively, one is computing the irradiance on the ground plane, which can be obtained by integrating the lighting over all incident directions. But some directions will be blocked, and determining which directions are blocked versus not blocked requires integration. We will be studying Monte Carlo integration in this lecture. The Monte Carlo algorithms are based on statistical sampling and random numbers. They were coined in the beginning of the 1940s. The term Monte Carlo originated in discussing neutron transport and nuclear simulations. Many of the great minds, such as von Neumann, Ulam, and Metropolis, worked on these problems. The canonical example we will consider is a one-dimensional integral done numerically. It can be done by choosing a set of random points to evaluate the function and then averaging them or taking the expectation or a statistical average. Monte Carlo algorithms have many advantages. In the computer graphics context, they are robust for complex integrals in computer graphics. These integrals can have irregular domains, they can have shadow discontinuities, and so on. Monte Carlo integration is also efficient for high-dimensional integrals common in computer graphics, where you might be integrating across an area light source for soft shadows, across the area of the pixel for anti-aliasing, across all incident directions for global illumination, and so on. Furthermore, the Monte Carlo algorithms are often quite simple to implement. They work for general scenes and surfaces, and they are relatively easy to reason about. However, care must be taken in terms of statistical bias. In practice, there is a lot of care to ensure your Monte Carlo algorithms are unbiased and do in fact produce the correct result. However, Monte Carlo does have its disadvantages. It can be a noisy technique. It can be slow, that means you need multiple samples for convergence. In fact, Monte Carlo should not be used if alternative analytic approaches exist, but they seldom do, which is why we have to study Monte Carlo integration in this course. We will begin by talking about 1D integration. Here you have a function f of x. For simplicity, let's say x goes from 0 to 1. You are trying to find the integral from 0 to 1 of f of x dx. One way in which you can do it is approximate the function f of x by some function g of x, which is easier to integrate. In fact, the standard integration methods like the trapezoidal rule, the Simpson's rule, effectively do this. They form a piecewise approximation to f of x and then integrate the resulting trapezoids, for example. These rules converge very efficiently for smooth integrals and they are deterministic. However, they are not very useful in computer graphics because the convergence analysis and the error analysis breaks down in integrals with discontinuities. Furthermore, If you have to do this in each dimension with a high-dimensional integral which can easily be 8D or even higher in some graphics problems, you can rapidly lead to the curse of dimensionality where the complexity is actually exponential with the number of dimensions. Monte Carlo integration is an alternative approach where instead of finding this approximating function deterministically and integrating, instead one tries to do it in a statistical way. We find the expected value or expectation of the function f of x. You can imagine simply choosing sample points along x randomly, and then the expected value of f of x can be obtained by simply taking the mean of these sample points. The estimator is this f of xi at each of the sample points xi, while you normalize by dividing by the number of samples, hence this 1 over n. This method is robust for discontinuities. It converges reasonably efficiently for large numbers of dimensions. It can handle many of the complexities in computer graphics, such as complex geometry and difficult integrals. And it is relatively simple to reason about and implement. One simply chooses a number of random points and then takes their statistical average or expectation. If instead of going from 0 to 1, you're going from region A to B, there's no problem with that. The normalization is just somewhat different. You have to consider the range of the domain B minus A and then normalize by the number of samples n. Of course, if we were just doing 1D integration, we would not really necessarily need Monte Carlo. The traditional integration methods are quite effective and the benefits of Monte Carlo would not be that significant. However, Monte Carlo is a real win when talking about multidimensional integration. In computer graphics, one often has an integral over many dimensions. I've called it ugly here, but it can involve pixel areas, surfaces, projected areas, angular directions, camera apertures, over the main lens of a camera, over time for motion blur, over the space of all integration paths. In fact, these domains also do not need to be regular. They may have fairly irregular shapes.